Okay, so again, good morning to everyone. So today we have lecture 2. So yesterday we derived, let's say, the ADS-CFT correspondence in its most well-known form, starting from the physics of D-branes. And so we have seen that the two main ingredients here are anti-de Sitter spacetimes and conformal field theory. And so this lecture will be devoted to introducing some of the key features of these two basic ingredients that we will need in the following. So let me start from anti-de Sitter spacetimes. Oops. Okay, so the D+1 dimensional ADS metric, which generalizes the metric that we have found in the near horizon limit of n D3 branes, is the following. So this denotes D-dimensional Minkowski. And so, as we said, R is the curvature radius of the solution. And the radial coordinates are small r spans from 0 to infinity. And so if we just want to make a simple drawing, so we have a semi-infinite line R, which is foliated by D-dimensional Minkowski at each fixed value. And we have an R dependent scale factor. And as R goes to infinity, we reach the, the scale factor blows up. Oops, I forgot, sorry, a square, of course. Yeah. So the scale factor blows up. And this is the so-called ADS boundary that we will see a bit better in a moment. And so in general relativity, ADS spacetimes are maximally symmetric solutions of Einstein's equation with negative cosmological constant. So it's a maximally symmetric solution with negative cosmological constant. And so we can derive it from the Einstein-Hilbert action, where this is the D+1 dimensional Newton constant. And here is the, so curly R is the Ricci scalar, not to confuse it with the radius of curvature. And negative cosmological constant. So from these, we can derive, of course, Einstein's equations. And then taking the trace of this equation, we find that indeed the curvature scalar, so the Ricci, is constant. So it's a constant curvature solution, which, if we use the relation that we have seen yesterday between the cosmological constant and the ADS radius, is the following. So, okay, so indeed, being a maximally symmetric solution with negative cosmological constant, it has a negative constant curvature scalar. Also, it also implies that we can write the Riemann entirely in terms of the Ricci scalar. So we can write here. And it has the maximal number of linearly independent Killing vectors. So the number of isometries is maximal. And it's given by, for a d+1 dimensional spacetime, it's 1/2 d+1, d+2. And we will see better what these isometries are in a moment. We will need them. And of course, so this is the maximally symmetric solution with negative cosmological constant in the same way as Minkowski is for 0 cosmological constant, or the Sitter spacetimes are for positive cosmological constant, or spheres are again for positive cosmological constants in Euclidean. Okay. So this is one set of coordinates that we will often use. And so another convenient set of coordinates is the following, completely equivalent, in which we just redefine the radial coordinate in this way. And so now again, z goes from 0 to infinity, and the ADS boundary is now at z equals 0. And so if we write it explicitly, so this is again a Minkowski foliation at any fixed z, and it makes it explicit that the metric is conformally flat. And so these two metrics that we will often use, they only cover a portion of the entire ADS spacetime, and this portion is known as the Poincaré patch. And so, so there is a boundary, which, as I said, we will see a bit better in a moment, at r going to infinity or z going to 0. And there is also a Poincaré horizon at r equals 0 or z going to infinity. And this is an horizon because we have a degenerate Killing vectors. So the time Killing vector becomes null at this value of the radial coordinate, but this is not a singularity. And it just signals that the parameterization that we are using is not global, but the metric can still be continued past this horizon. And so to actually cover the entire spacetime, as we will see clearly when we will draw the conformal diagram of the spacetime, we actually need infinite copies of this Poincaré patch. So if we want to parameterize ADS globally, we can do it starting with the hyperboloid, write it in a higher dimensional spacetime. So we can write it as the of this hyperboloid. So in a flat space-time with signature to comma d. So we have two time-like directions. So well, okay, let me also write the matrix. And so, for example, just to visualize it, which is very easy, if you take d plus 1 equal 2, so this is just minus x naught squared plus x1 squared minus x2 squared equal to minus r squared. And so for any fixed x1, we have a circle. So if we draw it, this is x naught, this is x1, and x2. And so we can visualize ADS in this higher dimensional embedding as this hyperboloid. So given this description, it's easy to recover the coordinates that we were using before. So if we want to cover the Poincaré patch, so with Poincaré coordinates r, xi, and t, it's enough to just set x naught to 1/2. Well, as you can verify by yourself, I will just give you the expression since we might need to use this embedding in the following. Because sometimes it's useful to actually translate everything in this higher dimensional space for XD. Square as well. Typo. Okay, so if we so we substitute this into the matrix that we had, we will recover the Poincaré patch matrix that we wrote before. And let me point out that, as you can see from here, R is given by x naught plus xd. And so R goes from 0 to infinity. And so this corresponds to the patch x naught plus xd positive. And so indeed we see that this does not cover the entire hyperboloid, as we were saying before. And so these Poincaré coordinates only cover a portion of space. So if we want instead a global parameterization, we use global coordinates. And so for that, we fix x0 square plus xt plus 1 square to be a circle of radius r squared plus 1 times r squared, where this small r is now a different r from the one that I was using before for the Poincare coordinates. And so if we substitute in the hyperboloid equation, this tells us that the other coordinates parameterize a sphere. So this is the d minus 1 dimensional sphere with radius r times, well, small r times capital R. And so we can simply parameterize the circle in this way. And so cosine tau and sin tau, and well, the d minus 1 dimensional sphere as usual. And so then substituting in the metric, we find that the induced metric is the following. And again, if you want, you can check it explicitly for yourself. And so this is the metric on a d minus 1 dimensional sphere. And so now, again, the radial coordinates goes from 0 to infinity, but the time coordinate tau is periodic. And so this set of coordinates, they cover the hyperboloid exactly once, and thus for these reasons are known as global coordinates, and these we will also very often use. And so, however, since time is periodic here, there are closed time-like curves. And so, of course, this is not ideal, but since the metric is tau independent, we can actually easily obtain a causal spacetime by just taking the universal covering of this metric. So we just extend tau from minus infinity to infinity. And so, strictly speaking, these are an infinite number of copies of what is defined to be ADS spacetime. But from now onwards, as it's also usually done, when we will refer to the ADS metric, we will actually have in mind this universal covering. Okay. Okay, let me so make some comments about the boundary of this spacetime. Okay, so as we said, as r goes to infinity, we find the ADS boundary. So let's see what that is. So this corresponds, if we look back, to taking all x0, xt plus 1, and all the other xi to infinity as well. And so, so going back to the equation for the hyperboloid that we had, so we can look at this limit by taking the rescaling, the following rescaling. So let me just write all coordinates x as lambda times x tilde, and take lambda to infinity. And so then the equation of the hyperboloid becomes the following. So here I clearly goes from 1 to d. Which goes to 0 as we send lambda to infinity. And so the boundary is defined by the condition x0 squared plus psi squared equal, no, sorry, plus x b plus 1. And we also have that this is equivalent under rescaling. So we also have the equivalence. And so these conditions define a d-dimensional manifold, so the ADS boundary, which has the topology of S1 times SD minus 1. And so this we can easily see, for instance, by exploiting the invariance under rescaling to fix x naught square plus xd plus 1 square equal to 1, which is at the same equal to time equal to the sum over the xi squared. And so, so this is the S1 and this is the SD minus 1. And indeed, we can easily see this topology in global coordinates. If we go back to the metric, so where tau was compact, by just taking the r to infinity limit. So then we're left with the indeed with the S1 and the SD minus 1 factor. And so, so the universal covering does have a boundary which is simply which topology is R times S d minus 1. And so this boundary is actually said to be conformal because essentially we have a whole class of boundary matrix which are related one into the other by conformal transformation. And so this induces a conformal structure that is an equivalent class of matrix which are related by conformal transformations. So this is the boundary for global coordinates, for Poincare coordinates. So this is for global. For Poincare coordinates instead, as you can see easily, let's say for instance from this form, as we take z to 0, the boundary is instead d-dimensional Minkowski. Okay, so I guess that's pretty easy. So, well, as usual, if you have questions, please ask. Okay, so if you want to study the causal structure of the spacetime, it's convenient to introduce the following coordinate. So, so we take the global coordinates and we define R to be the tangent of a coordinate throw, which then goes from 0 pi over 2. And so then the metric becomes the following. And so in these coordinates, the center of ADS is at rho equals 0, and the boundary is at rho going to pi over 2. And the boundary geometry is well, the R times the D minus 1 dimensional sphere. And of course, the causal structure doesn't change if we take a conformal rescaling of the metric. And so we consider the conformally equivalent metric, this square minus theta square plus. And so this metric is almost R times a d-dimensional sphere, and almost because the now the radial coordinate rho only goes from 0 to pi over 2 and not to pi. So essentially, for any fixed tau, the spacetime is now a semisphere. And so, well, from this expression, it's easy to now to draw the Cartan-Penrose diagram of the spacetime, which is essentially a field cylinder, which we obtain by revolving a strip which extends between 0 and pi over 2 in the radial rho coordinate, and which rotates around its axis. So let me draw it. This is the rho equals 0. So then we take strip till rho equals pi over 2, and this rotates around the axis and fills, well, and spans this field cylinder. Okay, so this is the radial coordinate rho. So this is time. And these are the angular coordinates. And so the boundary of this cylinder at rho equal to pi over 2 is the ADS boundary, which is a cylinder. So it's R times S d minus 1. Okay, let me make us another drawing, which is just a cross section of this cylinder, because that's easier to make geodesics. So this is okay, rho equals 0, this is over 2. And so this will be, well, along, let's say, some angular coordinate theta, this will be like theta equals 0 and theta equal pi. And so now let's take tau equals 0, for instance. And so now if we consider a radial light ray, so this travels at 45 degrees on the Cartan-Penrose diagram. And so we see that, for instance, a radial light ray which starts from the center will reach the boundary of ADS at a time tau equal rho equal pi over 2. And so essentially, so given the fact that in this spacetime we have a time-like boundary, and light rays can reach this boundary in some finite proper time, we need to specify boundary conditions at the conformal boundary of spacetime. And this is very important in ADS. So we need to impose boundary conditions. So for instance, if we impose fully reflecting boundary conditions, that is, we do not let anything to leak through the boundary, this light ray would completely reflect and then continue to bounce forever between the ADS boundary, well, bouncing, yeah, at the ADS boundary. So this is for light rays, and this you can easily check yourself. If you just write down the geodesic equation in ADS, you can easily verify, find the solutions and verify this fact. And similarly, you can also verify that if instead consider massive particles, they will never reach the boundary. So again, for a massive particle which starts at the center at I equals 0, this will follow a trajectory of this type. So they never reach the boundary, and they would continue to oscillate in the ADS interior. And so for this reason, often people refer to ADS spacetimes as a confining box of size R. And that's because of this effect on geodesics. And so this was the global metric. So if we want to draw the Poincare patch, this, so let me just draw it again. So the cross section of the global Penrose diagram. And so the Poincare patch is just this region. So in the R Poincare R parameterization that we used, so this will be the Poincare horizon. And as you see, it's clear here that we can continue space-time past it. And this will be the ADS boundary. And then we can draw, well, we can draw T constant surfaces. And the R equal constant surfaces. And so if we just draw it on the full Penrose diagram, on the cylinder, this will just cover this portion of the entire spacetime. And so it's clear that we do need, well, the global ADS contains an infinite number of copies of the Poincare patch. Okay. So if there are no questions, I will move to the to reviewing a bit better the symmetries of ADS.
I've got a quick question, if that's okay.
Sure.
Can you? Yeah.
Yeah, I see you.
So You said about imposing boundary conditions for light reflecting on the boundary, but I didn't understand where else could the light leak to?
Yes, so I guess, I mean, the standard boundary conditions are indeed fully reflecting.
Yeah.
But you could imagine putting the spacetime in contact with something else and try to continue the metric elsewhere. Like for instance, well, I guess one example that we can make that you will probably see is this for this analysis of the information paradox. What you would normally do is to put the system in infinity in contact with a thermal bath, so that they can measure the Hawking radiation, and that might allow also for some mixed boundary conditions. So of course, spacetime ends there. Well, yeah, reflecting boundary conditions are the natural choice, but you could consider putting the system in contact with also something else, and then you would need to specify. Yeah.
Okay, thank you.
Yeah. So I guess a priori you wouldn't know whether that's the actual end of spacetime or whether there might be something that depends on the system or on the physical problem that you are considering. Yeah. Okay, so let's come to the symmetries. And so actually by symmetry here, I just mean the isometries, so the coordinate transformation that leave the metric invariant. So we said that there is a maximal number of linearly independent Killing vectors, and we just want to see a bit better what they are, because then these will naturally lead to understand why we can think that the dual conformal field theory somehow lives on the conformal boundary of ADS spacetime. So to look at the symmetries, the easiest way is just to start from the, well, to just retake the hyperboloid equation that defines ADS. And so from this equation, it's clear that the ADS D+1 symmetry group is also D, 2. So indeed, the hyperboloid preserves Lorentz transformation in this space, which has a signature 2, D, but it breaks translations. So that's what is left. And so, well, to be more precise, as usual, as it is the case for Lorentz in Minkowski, the actual symmetry will be O to D, 2, but as it is usual, we take the restricted subgroup, which is connected to the identity. So we exclude the inversion. So we would like to see how is this how is this group realized in the Poincare patch. So for that, let me quickly rewrite the metric in the Z coordinate. So this is the dimensional flat space. Okay, so the isometries are the following. So we clearly have translations in the mu directions. with D generators. So we have Lorentz transformations in the same directions with 1/2 D -1 generators. And we have scaling transformations in which we rescale at the same time the axis and the Z coordinate, which is one generator. And then we have special conformal transformations, SCT, in which take Z and X with so B is a constant, and so this counts for D generators. And I should tell you also what A is. So this is Z square plus and so this is perhaps less familiar to some of you. So one way in which we can easily verify that this is an isometry of the spacetime is to observe that these special conformal transformations can be obtained by composing an inversion, a translation by B mu, and then another inversion. And so even though the inversion are outside the proper transformation, since we act with twice with the inversion, this belongs to the SO D, 2. And so just let me write explicitly the inversion, just in case you want to check it. So that will take Z into Z over A squared and X mu over A squared. Okay, so if we put everything together, we see that all the isometries which are connected to the identity generate indeed SD, 2, and that the number of generators indeed add up to 1/2 D plus 1, D plus 2, which is the maximal number that we can have in a D plus 1 dimensional space. Okay, so we will come back to these transformations soon. But before we do that, I also want to, well, just briefly introduce black holes in anti-de Sitter, because this will be used a lot in the following. So we will see well better the dictionary, I guess, on Monday. But so let me just say briefly that within the ADS-CFT correspondence, essentially there is a class of conformal field theory states which have well behaved geometric duals. And so in particular, empty ADS that we have just seen corresponds in the duality to the vacuum state of the dual field theory. And more in general, we can have some non-trivial, and we will see some example, asymptotically ADS D+1 geometries, which will correspond to excited states of the CFT. So above this CFT vacuum. So adding excitations in ADS, at least for a class of CFT states, corresponds to exciting the CFT above the vacuum. And well, I guess the simplest example of such excited states are black holes. So in particular, ADS black holes corresponds to the thermal state in the CFT, or states if we have more charges. Okay, so for that, clearly thermal states are fundamental, and that is also the case that black holes play a fundamental role here. So for that, let me write the metric and basic properties of these black holes. So this is are completely analogous to, they are analogous to black holes, Schwarzschild, or well, in the simplest example, Schwarzschild black holes in ADS. So if D is greater than 2, so from ADS4 onwards, we write the metric in the following way. And so here I want to include both black holes that have a spherical event horizon as well as planar black holes. So let me just write generically d sigma kappa squared. So the blackening factor F has the following form. So we have R squared plus kappa minus RH. So this is the radial location of the event horizon of these black holes. And so, so this d sigma kappa can be a sphere. Well, it's a sphere, d minus 1 dimensional sphere, unit sphere for kappa equal 1. So this will be like the analog, well, this will be like the global or Schwarzschild-like ADS black holes. And we can also consider black holes which have a planar event horizon, let's say dr squared, and this would correspond to setting kappa equal 0 in the blackening factor. So essentially this would be like for RH equals 0, this give global ADS or pointer ADS. So these are clearly they are static geometries, at least in the simplest form. And so let me draw the Perros diagram, which is the maximal extent, well, of the maximal extension of this spacetime. Okay, let's see. Okay, this is meant to be a bit bent. It's not a straight line. So here we have the ADS boundary are going to infinity. So this is the event horizon with the bifurcation surface. And so again, so constant R surfaces at this form, and constant T surfaces as before at the following. If we cross the horizon, as you see from the metric, time and radial coordinate exchange, because the blackening factor changes the overall sign. And so this is the curly line is the singularity, so that's R equals 0. And so if we, okay, so we start from the exterior region in which time goes up in this way, let's say, and then we can define a global time-like Killing vector, for instance, extending time in this way inside the event horizon, and then going down on the other asymptotic boundary, and then, for instance, like this. So this is to say that in the maximal extension, a constant time slice will have this form. And we can define time differently, and that's what we will see later. So actually, we can define it in such a way as such that it isn't actually globally defined. So for instance, we can take time running upwards on the other asymptotic boundary. So this will define a time-dependent state. And as we will see, this time-dependent state is particularly important, and it represents the geometric description of the so-called thermofield double state, or let's say one possible time evolution extension of the thermofield double state, which plays an important role. Okay. And well, just for future reference, let me also write down the thermodynamical quantities of this solution. So as usual, we can associate a temperature to the event horizon. So the temperature of this dual thermal ensemble in the CFT would be following. And well, for simplicity, I will just set the ADS radius to 1 in these expressions to carry out to around too many factors. So let's with R equal 1. We can associate a knock-in temperature given by the area of the event horizon. So let me just denote the volume of the sphere, or the regularized volume of the planar event horizon by omega k. And so that's just over 4G Newton times RH to the d minus 1. And of course, we can also compute the mass, which is d minus 1. Okay. RH d minus 2, RH square plus k. And okay, so before we end this review of ADS systems, let me also just say briefly that in d equal 2, so in ADS3, even though three-dimensional gravity is effectively non-dynamical, so there are no dynamical degrees of freedom, because the dimension is too low, still there are black hole-like solutions, and these were first found by Bagnato, Steitelbaum, and Zanelli, and are known as BTZ black holes. And so again, given the specific nature of gravity in 3D, these are effectively, they can be obtained as an orbifold of the vacuum ADS3 solution, as it is the case for all vacuum solutions in 3 dimensions with a negative cosmological constant. And there is a very easy map, well, to CFT quantities, but okay, that we don't need for the moment. I just want to say that these are very simple special solution and an ideal ground to test ideas. And so in this case, the blackening factor is the following. So it's the same metric and just a very simple blackening factor, and as it was actually found surprisingly, well, relatively recently, the Cartan-Pervas diagram of this space-time is the following. So the singularity is flat. It doesn't bend. And okay, so maybe this is actually a good moment to take a break. And so I will actually pause the recording. Okay, so let's move to the second part. So the conformal group in Minkowski. To start with. So we have seen the ADS isometries. And so let's now consider the, again, the ADS Poincaré patch, and with boundary at Z going to 0. Boundary. And let's look at the action of these isometries on the boundary. So, so maybe for that, I should just copy what I had before. So this was the action in the bulk. And so clearly on the boundary, we will still have the Poincaré, so we will still have the translations in the boundary directions, the Lorentz transformations, and let me write also the basically the generators, mu and mu nu. We will still have this scaling or dilatation, but let me suppress the bulk coordinate. And so this with generator D. And we have the, let's say, the reduction on the boundary of the special conformal transformations. And so now this A squared at Z equals 0, it's simply X squared. And okay, and so these the generators, the kappa mu with a note. So essentially what we see is that on the boundary of D plus one dimensional, of the D plus one dimensional ADS Poincaré patch, which is Minkowski, D-dimensional Minkowski, the ADS bulk isometries, so SO D, 2, they act as the part connected to the identity of the D-dimensional conformal group. So in particular, this dilatation and spatial conformal transformations, they are not Minkowski isometries, and that's what makes the extension to the conformal group. And so let me just remind you that conformal transformations are the coordinate transformation x mu, x prime mu, which rescale the metric up to an overall positive function. So they rescale the flat eta mu metric to G mu, which is eta mu. And so this group, as we have seen, just seen it, it's finite dimensional. We counted the generators, except that in D equal 2, where you've seen, as you've seen in the string theory course, in 2-dimensional, the symmetry is actually infinite dimensional. We have 2 copies of Virasoro symmetry. And so a much richer, an even richer structure than the conformal group in higher dimension. So since you have seen already quite a bit, I believe, of conformal field theories in 2 dimensions, here I will just mention some properties of conformal field theories in D greater than 2. So we see that on the boundary, the ADS isometries, they act as the conformal group. And so in that sense, we can somehow think of the dual conformal field theory as being defined on the ADS boundary itself. So the boundary is Minkowski D, the conformal field theory is in a dimensional Minkowski, and we have this nice reduction of the ADS isometries to the conformal symmetry on the boundary. So this is fine. That's often what we say. We talk about conformal field theory living on the boundary of ADS. And one point that I just think it's very important to stress is that, I mean, we have to keep in mind that these 2 theories, I mean, it's fine to think this way, but these 2 theories, they do not coexist at the same time. I mean, it's not that we have a bulk theory in ADS together with a conformal field theory on the boundary. So these are, it's a duality. So these are 2 alternative descriptions. They're not coexisting at the same time. Okay, so let's come to now to some properties of conformal field theories that we will need. CFT. So a quantum field theory, which is invariant under the action of the conformal group, is a conformal field theory. And so even though there are many classical scale invariant quantum field theories, meaning quantum field theories which are invariant under rescalings, we know that it's much harder to actually have an invariance also at the quantum level. So, well, for example, probably you have seen it already in the other course, but in any case, so for example, you know that SUN Yang-Mills in 3+1 dimensions is classically scale invariant because it has a dimensionless coupling. But quantistically, it loses scale invariance. And so quantistically, we have a beta function, which is running. And this is because of dimensional transmutation. So once we introduce a scale in the theory for to regulate the theory, this introduces a scale, and then often, well, then the theory doesn't have any more dimensionless parameters, and the beta function might be running. So this is just to recall that while at the classical level, this is easy to realize, it's much harder at the quantum level. And so in general, conformal field theories, as you all probably know, they arise in two types of situations. So they can arise as fixed points of the renormalization group flow. At which the beta function vanishes. Or as it is the case also for the theory that we've seen, so n equal 4 super Young Mills, they can be they can arise from finite theories. So n equal 4 Mills, for which the beta function vanishes identically for any value of the coupling. So for instance, for n equal 4 super Young Mills, we have a line of fixed points. And more in general, if we have a manifold, which is parameterized by the couplings of our theory, we can have sub-manifolds or manifolds of fixed points. And so in general, but this is not a precise example statement, I mean, there exist counter examples, but in general, it is more or less safe to think that unitary interacting quantum field theories, which are scale invariant, are also conformal invariant. So let me put quotation marks because that's not a precise statement. I mean, there are counter examples. And so in a conformal field theory, the algebra of the conformal group is preserved also at the quantum level. And so now bear with me as I write down the algebra. Okay, so we have the Poincare part, so mu nu and rho sigma. So Lorentz, so P mu transforms as a vector, translations commute. And then the generator kappa of special conformal transformation transforms also as a vector. Mu rho. Mu. I won't write it, I mean, you can find it in all references. Two special conformal transformations commute. They don't commute with the lattitions. Sorry, what am I writing? No, I'm not there yet. So P mu with translations. The generator of dilatation is a scalar. And okay, so these are the two most important now commutators, and so dilatation and translations give translation, and with special conformal transformation, we get a special conformal transformation. And so, okay, so these are the commutators in terms of the generators that we wrote before. And one can check easily explicitly that this algebra is indeed isomorphic to the algebra of SOD, 2. And for that, one can check it by defining the antisymmetric generators, J, A, B, where now A, B go from 0 to B plus 1 in this way. B plus 1, 2, J mu D. And J D plus 1. And so now they satisfy the relevant algebra. So JAB, JCD, I, beta, AC, JD plus or minus permutations. And so now eta bar is the diagonal metric with signature 2, D. So minus 1, 1, 1, minus 1. Okay. And clearly, the vacuum of the conformal field theory will be annihilated by all these generators. Okay, so I guess this I will skip. Okay, and so now let's see, let's say what are the relevant representations that we use. The physically interesting representations, and what are the main physical observables that we use in the conformal field theory. So we will talk about primary operators and correlation functions. So in general, in quantum field theory, we are used to identify particles by their mass and their Lorentz quantum numbers, which correspond to the Casimirs of the Poincare group. However, in presence of conformal symmetry, this is not anymore possible because the p-squared operator, so the mass, does not commute with the other generators. So for example, as we have seen, it does not commute with the dilatation. And so it's not anymore a Casimir for the conformal group. And indeed, if we apply a conformal transformation, essentially we can rescale mass and energy arbitrarily. And so if a state, if a representation contains a state of some fixed energy, it will also contain states of arbitrary energy which go from 0 to infinity, and that we can achieve by applying the dilatations. And so essentially the spectrum will be continuous, with masses from 0 to infinity. And so, so given this observation, the entire S-matrix formalism that we normally use in quantum field theory is not suitable in this context. And what we use instead are correlators. So the physically interesting physics of conformal field theories, or well, most of it, is encoded in correlation functions. And so, well, so from that point of view, the representations that are of physical, or mostly of physical interested, are characterized by operators or fields, which are eigenstate of the dilatation operator. So they satisfy this commutation relation, and this is at x equals 0. So as usual, one can start to build the representation at the origin, and then move it away from the origin by applying translations. So they satisfy this commutation relation, minus I delta O. And so this delta is the eigenvalue for the dilatation, and which is known as conformal dimension, as I guess you have seen already. Sure, already. And so let me just stress one point, which I guess you're also familiar with, is that in this context, when we might talk about fields and operators interchangeably. So what we mean here by fields is still local operators. So these will include also the actual fields that might appear in a Lagrangian or in the path integral measure if a Lagrangian description is available. But they also, by fields or interchangeably operator, we mean also all products, all other operators that we can obtain by acting with products and derivatives. And so, okay, so coming back here, so the finite version of this commutator says that under the scalings, so for x going to x prime equal to lambda x, O transforms in this way. Over x. And so then, as I was mentioning, to build a representation, these computational relations are particularly useful because just by applying these computational relations, you can easily check that the action of the p mu of translation increases the scaling dimension of the operator by 1 unit, while the action of the Peschel conformal transformation decreases by 1 unit, so like raising and lowering. And moreover, in unitary quantum field theories, we also have unitarity bounds, which essentially mean a lower limit on the dimension of the fields, which are allowed by requiring that all states have a non-negative, all states in the representation have a non-negative norm. And so, for instance, for the scalars, and let me just stick for simplicity to scalars in what I would write. We could add variance indices, but it's easier. So for scalars, the unitarity bound is this following, which is saturated by a free field. So essentially, putting together these two informations, we can then build lowest weight representations by starting from operators of minimal dimension, which are annihilated at the origin by the action of the special conformal transformation. So and which are known as primaries. So then essentially so then the representation that we're interested in of the conformal group, they start with primaries, so they are labeled by their Lorentz quantum numbers and by their conformal dimension, which are the Casimir of the conformal group. And so, and then the whole representation is obtained by acting with P mu, which then raises the conformal dimension. And so all these other operators in the representations, which are obtained by acting on the primaries, are known as descendants. And so then the representation is indeed infinite dimensional, and it has a continuous spectrum of masses squared from 0 to infinity. And okay, and so this was the finite representation, transformation of under scaling. And then in general, under a general conformal transformation, the primaries transform in the following way. So as the Jacobian determinant, let's to the minus delta over d. And so, as we were saying, in a conformal field theory, all physics is encoded within correlators, and these are highly constrained by the symmetry. So, so let's have a look at what are the what is the form of correlators of primaries. And I will write it down in the case of scalars, otherwise there is some tensorial structure, which takes a long time to write it down. So in any case, so to see how conformal symmetry constrains correlators, so one can just start from the path integral computation of a generic correlator with insertions x1, x2, and so on. And so essentially by requiring that both the action and the functional integration measure are invariant under conformal transformation, we find that the correlator transforms covariantly under conformal transformation for the primaries. And well, you can try to check by yourself as an exercise. Then okay, well, for a one-point function, there is nothing to check. So for one-point function, we get the expectation values need to vanish, because otherwise a vacuum expectation value would just break dilatations. So for two-point functions, you can check that these fixes. So two-point function vanish for operators of different conformal dimension, and they are non-zero otherwise, and they have this form, which is fixed by conformal invariance. And so these C1, 2 are just some numbers that can be rescaled by fixing the normalization of the operators, and it's actually often convenient to work in a orthonormal basis in which these are delta functions. So then in this orthonormal basis, the two-point function would vanish if the two operators are not the same. And then again, conformal invariance also fixes almost fully the structure of three-point functions. Up to some coefficients, 3. This is delta 1 plus delta 2 minus delta 3. Let's go 3 is delta 2 plus delta 3 minus delta 1. Delta 1 minus delta 2. Where, okay, by this notation, it's familiar, so x1, 2 is x1 minus x2. And then if we want to obtain, so this is for primaries, if we want to obtain correlators of descendants, they are simply obtained by taking derivatives. And so these numbers here, which completely determine the three-point functions, are the OP coefficients from the operator product expansion that you must have seen in the string theory course. And so essentially, it turns out that actually these, well, the spectrum and these OP coefficients, Cij, so the set of all these PI coefficients actually constitute the entire data of the conformal field theory. So at least in principle, by knowing the scaling dimensions of the fields that appear, and their Lorentz quantum numbers, and all the OP coefficients, so the coefficients of the three-point function, we can in principle compute all correlators, all higher point correlators in a conformal field theory. And of course, this is at least in principle, because in practice it turns out to be quite hard, but well, it is still very powerful that all physical informations can be extracted from this set of numbers. So in particular, if we now look at 4-point functions, so this is the first correlator, which is highly constrained, but not completely fixed by conformal symmetry. So let me write it for shortness in the case in which the three conformal dimensions are the same. And so in this case, so I drop the 1. So we have like the leading OP singularities as 2 points come together. So x1, 2 to the minus delta, and x3, 4 to the minus delta. And then we have a function of the two cross ratios, u and v, that we can build given these 4 intersections. And so this function can be an arbitrary function of the two cross ratios. So the two cross ratios are the invariants, the two invariants that I can build given 4 insertions. So these are U, x1, 2 squared, x3, 4 squared, over 1, 3, 2, 4, and B. And so this is for 4 insertion. For n points, you can try to verify that this would entail n times n minus 3 over 2 independent cross ratios. So in any case, so the 4-point function is not completely fixed. So there is this arbitrary function of the cross ratios that can appear. And one convenient way to rewrite this correlator is to use a conformal block decomposition. So let me be slightly schematic, but so the main idea is to essentially use recursively the OPE inside correlators. So let me just denote the OPE in the following graphic way. So we write it as a sum, which is labeled by the contribution of the primary in the entire conformal family. So the primary alone, let's say, labels the contribution of the whole conformal family in this sum. See, 1, 2, O tilde. And let me just denote it graphically in this way, so the contribution of the family. And so essentially we take correlators, we can apply recursively the OPE, and that allows to reduce a correlator of n insertion to sums of 3-point functions, which are instead which are fixed by conformal symmetry. So, for instance, for the 4-point function that I wrote before, so we can take this arbitrary function of the cross ratio, and we can expand it using the OPE in so-called conformal partial waves. So we write f u of v. So we apply twice the OPE. And so we write it as a sum over conformal families. And so these labels the intermediate states that can that are present in the OPE of the two operators O. And then we have twice the OPE coefficient, so the square of the OPE coefficient. And this is because, as we have said, there cannot be non-diagonal terms because their 2-point function would be vanishing. So the 2-point function that only doesn't vanish for equal operators in the orthonormal basis. And a function g of the two cross ratio, which is the conformal, which are the conformal blocks. So I will also make some precision, but okay. So the idea is that this function, which appears, it's completely fixed by conformal invariance. So it's the part, the ingredients of the correlators, which are completely fixed by conformal invariance. They depend on the spin and conformal dimensions of the external operators O, as well on the conformal dimension and spin of the exchanged operator O tilde, and on the two cross ratios. And so, so diagrammatically, which might be helpful, because unfortunately I don't have enough time to actually show you how all this is derived. So diagrammatically, we are decomposing the correlator in this way by summing over intermediate exchanges. So this would be the 4 insertion or X1. And we have these two interactions, which are the two OPEs that we have used and which bring two OPE coefficients. And so, so this type of decomposition in conformal blocks is often particularly useful, actually, when we want to try to work out some general considerations. I mean, if we know, if we have some information about the spectrum and the structure of these OPE coefficients, we can deduce, at least in some, often in some approximate ways, some information about the full correlator. So in particular, these conformal blocks are known to some extent. So they definitely have a double power series expansion. So if we take the two operators to come together, we know how to write the OPE, and that gives us the this power series expansion. There are known recursion relations for these conformal blocks, which also allow for some rational approximation of the blocks, which can then be used for numerics. They also have integral representations, which were worked out by Ferrara, Grillo, Gatto, and Parisi quite some time ago. And in even dimensions, they are also known explicitly in terms of hypergeometric functions, and these expressions were worked out by Dolan and Osborne. And just one observation that I want to, well, two more actually observations that I want to make, and then I will stop about these blocks, is that so the dominant, the identity always, the identity operator always appears in the OPE of two equal operators, two identical operators. So it appears in the OPE of O. It has OPE coefficient equal to 1. So COO identity is 1. And in D greater than 2, it has no descendants. This is different in 2 dimension, in which we have the entire family of the identity, which includes the energy momentum tensor and its derivatives. But okay, in D equal 2, there is just the identity. And so this is also the most singular contribution, as you see going back here by looking at this refactor. So all the other higher order terms will be less singular. And so this identity in this type of correlators is the dominant contribution, the most singular, and that often actually already the knowledge of this very basic fact allows to extract some very interesting physics. And I believe you will see some examples of these results in the entanglement entropy, or let's say entanglement measures lectures. And the other observation that I want to make is that clearly I decompose the correlator in this way. So in a particular channel, we say, in which I contracted, I use the OPE between the insertion at F1 and the one at X2 and the one at X3 and X4. I could have chosen to decompose it in any other way. And so that translates into constraints that these correlators need to satisfy, which are known as crossing symmetry. Which mean, again, let me do it diagrammatically. It means that, for instance, this type of blocks decomposition should also be equivalent to the channel in which I first contract 1 and 4, and then 2 and 3. And so this is just amounts to say changing the order of these cross ratios in the conformal block of the intermediate states. And so this type of constraints are actually very powerful, and they are used to obtain the constraints on the spectrum of in the space of quantum field theories to single out conformal points. So in particular, they used to actually rule out spectrum which are inconsistent with conformal field theory. And well, this observation plus many others, but this is the very basic one, are at the basis of the so-called conformal bootstrap approach, which I'm sure you have heard about. Okay, I'm sorry I went slightly over time, but I think for today we can stop here. So